Okay, there it is. So here's the quiz for the people. You guys can get a little jump on it, I guess. But let me go ahead and give you this. There's two for you. You only get one. Sorry. Need two here. I think there's two. There, maybe three. There you go. There's two. That's not enough. I'll give you one. You've got 2 minutes left. I want to make sure that you're. There's 2 minutes left. Oh, thank you. I'll come back for the extras. So give it a go, and then we'll do the answers here in a bit. Okay. You don't need this. Try something. Oh, you got extras. Thank you. Thanks. All right. So many answers. Oh. Manage. Who snuck in? 11. Wow, I see some people are excited to be done. If you are done, feel free to pass yours over. If you're still working, don't worry. I know some people want to savor the experience more than others. This one's relatively quick. All set, Mason? Yeah. I want to rush you. Sure. Wait, you live on campus? Okay, yeah, Steve Campus close right now. So, you can call. Yeah, it's illegal. You all set? All right. No, I'm not. I don't want to make you nervous. I'm going to go over. I'll give Blair one here. You can take a minute, see if you can whip this off. I know you can. Do your best. Throw something down. Put some lines on there at the very least. What's that? Yeah. I didn't want to make everyone nervous. Most of you are doing perfect, so doing a great job. Yeah, put some numbers down. Good. That's what I'm looking for. All right, wrapping it up. Some lines, got some numbers. That's the best I can afford. What do you think? Got something? Got a line? You have some lines and numbers? Wait, you want me to do it? Sort yours out? It's only a quiz, it's worth almost nothing, so it's fine. Let's see who's left. Who's left? You got one? All right, great. Give you hints as well if you want. Did you have any numbers or lines? You could put lines there at the very least, couldn't you? There's the 181 and 103 coming down there. Good job. And 103 would be over here somewhere. Good job. And then what's this one? 143 down here somewhere? Yeah, that gets it started. Yeah, so, yeah, I know you didn't get as much time, but it's all close. Nice. Yeah, you know what's going on, right? Yeah, I mean, now I could use yours as the key. Basically, yeah, you've got most of it there. Thank you. All right, I think I got them all. Do I have anyone holding out on me? Okay, excellent. Let's take a look at this, see if we can do this together. So the first one, 81 to 103. Let's go ahead and draw those lines on here. Is that showing up? It is. So you have $81 down here, 103. You might say, why did I do that? Well, it's because 92 is in the middle, and you have $11 on either side. That's one standard deviation. And so if you remember, the empirical rule says that 68% is one standard deviation away from the middle. So 68% belong between those. So that's the answer to that one. 68% is in the middle. And then down here, more than 114. What? Where is 114? Well, let's start counting. 92 on my calculator plus 11 is 103. Plus another 11 is 114. Okay, so that's this line. I'm interested in this little tiny sliver over here. So that's who I'm really interested in, but I better figure out exactly what's happening here. So let's subtract 11 and subtract another 11, and you get down to 70. And this is 95%. How do I know? Well, the empirical rule says 95% goes in the middle two standard deviations. So if that's 95%, then what's outside must be 5%. Because if it's not inside, it's outside 5%. And then, well, that's half, because these are pretty much the same shape, that over there. So this will be 2.5%. And that's going to be the answer there. So I saw a lot of 2.5%, a lot of 68%, and then a lot of people, thank you for labeling and drawing something, the lines. You know, that's worth at least half to have, you know, thought through that. So so that was a good job that you did, even if you didn't get the number right. If you've got sort of the general idea of what's going on, you're going to be in good shape. Okay, we're moving on though. Today we get, oh, so exciting. One of my favorite topics is probability. If we have time, I'll do some magic for you, because that's part of the probability thing. Here's some probability questions. Just jot down your answers, what you think that this is. Just take a sec. So based on your expertise, what do you think the probability is that it will rain today? Yeah, go ahead and just put down something. We'll check. Not to worry. What's the probability you'll get an A in this class? So just based on your knowledge of statistics, how difficult it is, maybe you've already got a feeling for the likelihood. Well, what's the probability that you will win the Powerball lottery? Is that a thing still? Seems like they keep changing the name of this thing. But go ahead and jot down, what do you think the probability that you will win the Powerball lottery? What's that? And then finally, I know this is getting a little bit dark. What's the probability that you will die during the next year? So go ahead and just take a guess. I mean, if you prefer not to think of death, you could say, what's the probability you won't die? Just do it that way. You know, they're related, of course. So take a guess for these 4 probabilities. I will show you the answers, or at least the estimated answers, in a bit. Even the 4th one. We'll deal with that in just a bit. But before we do that, we need to talk about the difference between what we call empirical probability and theoretical probability. Theoretical probability is something you've studied, I'm sure, because everyone here can tell me, if I roll this die, what is the probability it comes up a 6? So I roll the die, probability of 6. You know what it is, right? Go ahead, say it.
1 in 7.
Yeah, thank you. Thank you, brave person. It was a 6. What are the chances? 1 in 6. So I know. So not all that impressive, to be honest, you know, because you got a 1 in 6 chance that it's going to come up a 6. So I could do the same thing. What are the probability it comes up a 4? Oh my goodness! Actually, it is a 4. Now that is getting a little bit freaky here. Let me do one more for fun. I predict this will be a 3. It's a 5. Okay, so that breaks the streak. But anyway, yeah, so you know this general sort of idea of probabilities. You can talk about a deck of cards. If I take a deck of cards, I say pick a card, any card. What's the probability that you pick the ace of spades? Well, it's 1 in 52 if you know what a deck of cards is like. Now, if you don't know what a deck of cards looks like, don't fret. I can give you a deck of cards. I remember when I was teaching in Philadelphia, this is the 6 of clubs, by the way, I was doing this, this is years, decades ago, when I was your age, almost, a little bit older. I had a student come up to me after class and she said, I've never seen a deck of cards in my life. And this is Philadelphia, so you have a very diverse population. And so I was like, well, let me give you a deck of cards. Because we were doing probability. In the book, there were all these questions about decks of cards. So yeah, seriously, I do have plenty of decks of cards in my office if you need one. But we're not really going to be focusing on decks of cards that much. When we talk about theoretical probability, we're going to be using some language that we're going to learn now. But the other way of talking about probability is empirical probability. So this would be things like, what's the probability it will rain today? That's going to be an empirical probability because what weather forecasters do is they say, well, based on the conditions, looking at the history, the past of what has happened, here's what the probability of rain is today. So you sort of base your prediction. Same thing with this. Probability you get an A in this class, I'm going to tell you what the probability is based on previous classes. So I'll tell you what, like 2 years ago, what the probability, like basically what the ratio of A's was. This, though, we can use empirical probability. This is also going, or no, theoretical probability for Powerball. This is empirical. So dice, cards, things like that, we'll use what's called theoretical probability. And so this is just some basics. You'll have a few questions on this stuff, and then we'll move on your homework. But the main reason for doing this is to understand how probability relates to statistics. So I can only have so much fun today. So it's kind of sad for me. But hopefully you'll have some fun too. So starting off, if you think of something like a single birth, you have a child. Maybe you're planning on having a baby at some point in your lives. So if you have a single birth, the sample space, we're going to use the phrase sample space to describe all the things that could happen. Have a baby, it's either a boy or a girl. It's like a coin flip. So it's a boy or a girl. And that's it. Those are the only options. I know you're thinking, wait a minute, you could have twins. Okay, let's just assume you've gone to the first ultrasound. You see there's only one kid in there, okay? Anyway, so boy or girl. Let's say that you have 3 births. Maybe a better way to say this is you know someone who has 3 children. I have 3 children. And what are the different options? What are the options for the children? Well, you could have 3 boys. You could have 2 boys and a girl, but the girl could be the youngest, or the middle child, or where's the oldest? There, oldest girl. So there's different options for where the girl shows up. Or you could have 2 girls and a boy, and the girls could be younger than the boy, or sandwich the boy in between, or older than the boy. And these are very different situations. Maybe some of you are from a family of 3 kids, and you know, Like, if you're the youngest girl with 2 older brothers, that's way different than being the oldest girl with 2 younger brothers. I was in a family like this. I had an older sister, younger brother. And then, of course, this is my family, by the my kids. My kids are all girls, so I'm girl. So those are all the possibilities, and there's 8 of them, but it's like flipping coins. You know, if you're going to have 3 kids, there you go. Those are the different possibilities. So a sample space is just a list of all the different outcomes that could happen. So let's go ahead and try this yourselves. Jot down, you can discuss with your neighbor if you need to, what you think the sample space is for these experiments. Number 1, roll a 12-sided die. I've got one right here I can show you. So if I roll that, what are the different outcomes? You might say, it's printed with the numbers from 1 to 12, by the way. So I'll show you that. Ask a randomly chosen person, how many children have you had? Draw a card from a standard deck of cards and record its face value. All I mean there is, like here, this is a 5, or a 10, or a king, or an ace, that sort of thing. And then flip 3 coins, penny, nickel, or penny, diamond, quarter, record the orientation. Is it heads, tails for each one? So go ahead, see if you can write these down, and then we'll see how you did. Am I recording? Recording is happening. Bless you. There we go. So, unfreeze. Okay, I'm not giving you a lot of time. Oh yes, Caden.
I just have to ask.
It's a personal issue, so I'll just come back. Is it about the contracts?
Yeah, it's not.
Drawing the card.
Yeah. Okay, yeah.
2 through.
Otherwise, I'll forget.
But there are 3 suits in the 4 suits. 13 cards. So it would just be numbers.
All right, let's go ahead. Yeah, it had nothing to do with math. I was disappointed, but let's go ahead. Let's go ahead and see how we do with this. Evan, you know about rolling 12-sided dice, don't you? Dungeons and Dragons fan? Sure. All right. What are the different things that could happen when you roll a 12-sided die? Okay. And specifically, what are those? Okay, so 1, 2. Yeah, I know. I'm not even gonna write them all out. 11, 12. Yeah, you could get any of these. I've got my 12-sided die here in case you want to see it. Here it is. So you can see there's a 6. And look, isn't that nice? It has a dot to let you know that that's a 6 or 9 and this one's a 6, so you don't get confused. So there's the 12. So you've got all the different numbers that you could get. So very good. Okay, next one. Here we are. Ask a randomly chosen person how many children he or she has had. Let's do this. Alana, what are the different answers you might get out of a person? Okay, so to a lot. Yeah, now let me just stop you for a sec. I've done this in the past, and it seems like it's about a 50-50 chance that whoever I ask forgets about the 0 for one reason or another. They always start at 1, and I have to remind them, that there are a lot of people probably in this room who fit into that category. So well done at remembering the 0. So yeah, where do we stop this? I mean, here we stopped at 12. Well, I was kind of curious myself, so I looked it up in the Guinness Book of World Records to know where we could stop, and I'm curious to see what you think. So which of the following is the documented Guinness Book of World Records largest number of children born to one woman? Take a guess. Take a minute. All right, do you have your guess? Is it locked in? All right, so the right answer is 69. And here's the actual text from the Guinness Book of World Records. And I want to point something out. This woman doesn't even have a name. It's just the wife of Fyodor Vasilyev, a peasant from Shuya. This is back in the 1700s. But another thing that is astounding about this is this statement here, that in 27 confinements, that's 27 birthing events, she gave birth to 16 pairs of twins. You'd think she would learn after a few of these happening. 7 sets of triplets and 4 sets of quadruplets. It's incredible. I don't know how she survived all of that, but she did. And apparently, not only did she survive, but 67 of the 69 kids survived, because only 2 of the kids failed to survive their infancy. Infant mortality was a big deal back there in the 1700s. Shocking. And of course, you might be thinking, well, why do we restrict this to women? Well, it's because guys have a different situation. You know, like Genghis Khan supposedly sired half of Asia. And then you have this little statement. This was a footnote in the Guinness Book of World Records. So that's, it's an older copy, 1994, but I don't think it's changed. I'm guessing that no one is vying for this particular world record. Okay, drawing a card from a standard deck of cards. I've shown you this. Here's my deck. I can show you it again if we need to. But let's find someone to get this one. So what do we got? Nevaeh, what do you have for the sample space? What are the things that could happen if I give you one of these cards? Pick a card, any card. What are the things that you could end up getting out of this deck? You want me to do it for you? I could give you, here, how about this one? Oh, you can't see from back there. Yeah, Blair can see it for you. What's that? It's a J, Jack. Okay, so there's a Jack. That's one of them. I'll put it on the list just a second. So that's a possibility. Jack. Okay, let's see. What else do we got here? All right, what do you got? It's a 4, so you could have a 4, right? So that's what you're doing. What are the other things, do you know? Do I need to give you a deck of cards? 2 through 10. Okay, so 2, 3, 4, 5, up to 10. And then you've got the Jack, King, Queen, and then the Ace. Okay, so there it is. There's actually 13 different values, if you want to think of them as values for a deck of cards. So there's that. We'll save that. We'll do a magic trick with it if we have time. So there it is. Yeah, so there it is. Very nice. Now, I'm curious about the flipping 3 coins. What I've got up here are the most popular answers to my question. Flipping 3 coins, record the orientation of each. And so I'm guessing that you all have one of these 5 different answers. And I'm hoping that most of you have the correct answer. So the main thing is that flipping coins and having children is basically the same thing. Okay, not exactly the same thing. But in terms of probability, it's the same thing. And so it's this bottom one here, letter E. I know, it's way down at the bottom. Why is it so low? So you could have 3 heads. That's a head on the penny, a head on the dime, and a head on the quarter. And then it could be 2 heads and a tail, the quarter being the tail, or 2 heads and a tail where the dime is the tail, here the penny is the tail, and so on and so forth. So there are actually 8 different options there. Yeah, this is not right, even though true, each coin could be heads or tails, but it really doesn't encapsulate all the different things that could happen. So here's a list of all the things that could happen. Okay, the reason why it's a big deal to know about sample space is because to compute probabilities, theoretically, you need to know how many things are in the sample space. So here's the general formula. You learned this back in 9th grade or 7th grade, I don't know when, because you probably all can tell me, well, when I roll a die, what's the probability of getting a 4? So this, though, is the sort of the formula. Let's just get an example here. I have this 12-sided die. So on a 12-sided die, let me write this down, sided die. So you know the numbers from 1 to 12. I want to know the probability that you have a number that's less than 4. So I want to know what's the probability that you have a number less than 4. So let's use this formula. The formula says you do the number of different events or things, things in the sample space. So there's 12 different things that could happen. So there's 12 things. And then on top of my fraction, I want to know how many ways can whatever this is that I'm interested in, how many ways can it occur? So let me look at my die. And as I look around, I see the number 1, and I see the number 2. I see the number 3. Those are all less than 4. Yeah, that's it. 1, 2, and 3. Those are the only numbers less than 4. And so there are 3 different ways of having a number that's less than 4 on this die. And that would be the probability of getting a number. Now, there's a caveat to this, and that is that you can only use this rule if you have equally likely outcomes. So each of the either outcomes or simple events, however you want to say it, but each of the things that could happen should be equally likely. So just to demonstrate something that is not equally likely, let me show you this. This is one of the very first things I ever printed on 3D printers here at MVNU, and this was back before I had one of these myself. And you can see that it ran out of filament midway through the print, and whoever was managing the printer was like, oh, let's just throw a different color on there, which disappointed me because now it's both white and blue. But this is a shape called a cube octahedron, and you can see some of the sides are squares, some of the sides are triangles, and if I roll it, it's going to land on either a square or a triangle. But if you do this a few times, you start realizing that the squares are much more likely than the triangles. I'm going to be sitting here for a long time if I want to get it to land on a triangle. It's still a square. Yeah, it's going to be a bit. I've had it land on triangles, but it's very rare. It's very rare. So triangle and square are the 2 things that could happen, but they are certainly not equally likely. It's much more likely that you land on a square than a triangle. So that would be a situation where you can't use this rule. Whoops, wrong thing. There's the thing I want. So the only time you can use this rule is if you have equally likely outcomes. Fortunately for us, most of the things we deal with, at least on the homework, it's going to be pretty simple. You're not going to have to really think too much about it. Let's see. So we've got that. So let's see. We'll do. Yeah, I guess we can do this. Yeah, why not? Yeah. So let's. We've already done the 12-sided die. That's not too difficult. The probability of getting a 7 is 1 out of 12. Because on this 12-sided die, there's only one face that has a 7 on it. You can double check later if you really want to, but if you don't trust me. But there's one face that has a 7. All the rest of the faces have other numbers, and so there's a 1 out of 12 chance. Doing the cards, what is the probability of getting an ace? Well, Nevaeh said that there are 13 different outcomes, and that was 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King, and Ace. So there are 13 outcomes, and one of those is the ace. Another way of looking at it, though, is that there are 52 cards in a standard deck of cards, and of those 52 cards, 4 of them are aces, and they're all equally likely. So we're all good with that, hopefully. Now let's do this last one, because this last one's kind of surprising. If you flip 3 coins, what is the probability of getting 2 heads out of those 3 coins? Well, to do that, we have to refer back to that sample space, and I don't know, I can fix this. Give me a sec here. We refer back to this sample space here, and I'm just going to grab this image so that I don't have to scroll to the bottom of the page. Give me a sec. Done. Copy. Okay, let's do this. Back here. Paste. Okay, I want to know the probability of getting 2 heads. So what's the probability of 2 heads? Now, one of the things, and you might not believe me about this, we don't have to go into it now though, but these are all equally likely. It has to do with the fact that when you flip coins, they're independent of one another, so the dime doesn't know what's happening with the quarter, and the penny aren't linked in any way. And so each of these things are equally likely. So you'll just have to trust me on that fact. There are 8 of them. So 8 of them are equally likely. So all you have to do is figure out how many of those have 2 heads. So I'll put the 8 goes down there. And Lily's going to tell us how many of those have exactly 2 heads. There's 3? Oh yeah, there are 3. That's this one, and this one. There are 3 out of 8. So the probability of getting 2 heads when you flip 3 coins is 3 out of 8. Very nice. Okay, so this is all well and good. As long as I'm on this, I need to mention one more property before we go on to something else. One more property of probabilities, and I need more room, so I'm going to have to erase this guy. Sorry. Let me do it this way. Okay, so let's do it this way. I will do a little chart. You know I love charts, especially because we're in statistics. So number of heads, and this is going to be the probability over here. Okay, so if we have 0 heads, we'll do this. I'll do this, don't worry. Let's see, Lily said that it's 3 out of 8, is that right, for 2 heads? Okay, so 0 heads, the probability is 1 out of 8. And that's this one right there. Do you see that one there? Okay, 1 head, I think that's this one, and this one. That's 3 out of 8. And then 3 heads, there's only this one right there, and that's 1 out of 8. Now this is what I wanted to point out about this, is that with any probability distribution, which is what this is, all of these numbers, all of the probabilities, if you've accounted for everything, then the probabilities should add up to 100%. So the sum of that will equal 100% or 1, however you want to say it. Kind of makes sense that if you take anything that could happen, you've got this, that's, if you've got the whole list, then the total probability for everything is going to be 100%, 1. Okay, so that, I think there's a couple of problems on the homework that allude to that, so I didn't want you to get sidetracked with worry. Okay, but we do need to move on. So let's see, I'm going to skip that for now. Give me a sec. Yes, let's skip on to this. This is important. Statistics and probability. So you might wonder why we care. So why do we care? Well, it's because of the fact that statistics is all about probabilities. I know you don't believe me. So let me show you some statistics. And to do this, I need to bring up some more statistics you can use. I know I just did one on Monday, and you learned so much from it, but you get a second dose this week, which is unusual. Usually it's no more than 1 per week. But this week we get 2. So here's the statistics you can use. It comes from a study put out in the journal Neuronal Urodin, whatever, in 2011. This is a study called The Effects of Acute Increase in Urge to Void on Cognitive Functions in Healthy Adults. Okay, so what's going on here? Well, they took a bunch of guys. Is it guys? I don't know if it's guys. It's only 8, though. I'm always skeptical when you have so few, but this one is so good, I got to share it with you. Anyway, they basically had these people, I don't know if they're dudes or if they're women in there, and they had them drink 250 milliliters of water every 15 minutes until they could no longer hold it. So basically, can you imagine? They're like, okay, it's time, drink. They drink their cup, and they give them another cup. Okay, drink. So they do this for every 15 minutes until they're like, I can't hold it any longer. And then at that moment, they gave them like math tests or memory tests. And they're like, can you do the math or can you do the memory test? And it turned out that, not surprisingly, having an urge to void, that is, if you've got to pee really bad, it really has a negative effect on your memory. Like so I guess the lesson learned is, if you've got to go before a test, take care of business. because you don't want to have this hurting you. Anyway, the reason I bring this up is not so, well, it's because it's kind of funny that they would do this study. But yeah, here's the graph that they have. So this is the rating. I don't remember why there's two curves here, but how badly they did with their memory test, whatever it was. So you have like the number of mistakes that they made, and the mistakes go up and up. So you can, this is a long time, 150 minutes. So this is 150 minutes before they had to go, it was so bad that they had to run to the bathroom. So they were doing this for a long time apparently. But then, so when, just before they went to the bathroom, they were getting all sorts of things wrong on this test. And then after, so lesson that you can take away from this is if you're ready to take a test and you feel like you've got to go, it's much better to go because you don't want your memory to be hurt from not going. Okay, but that's not the reason why I have this here, other than, yeah, it is kind of funny and interesting, but it's because of this. This is the actual paper. And you can see the paper here, the results. Let me zoom in on the results a little bit. So you can see those results. Look, they've got all sorts of words and numbers, but there's one number in particular. Actually, this number shows up multiple times, and that's this. Riddled throughout this paper are statements like this. Let me just go back to the original paper. This isn't even just a portion of it. You can see it's here. P is less than 0.001. Here, P is greater than 0.05. P is greater than 0.05. Here's another one, P is less than 0.01. There are probability statements throughout this paper. Every paper that you read that includes statistics will have probability statements. And so those probability statements, they are important because they help us to understand what it is that the statistician did. So here's how, hopefully, I can demonstrate this. I've got a deck of cards here, and we will do a quick math magic trick. Let me pick a row. We're just going to go back here to this row with Amy. I need enough people, sorry. So Amy's going to take the deck, and she's going to cut it. Move, do you know how to cut a deck of cards? Do I need to demonstrate this? Okay, yeah, you separate, and then you complete the cut. Here, let me know. Just, here, okay, just so that everyone can see. Just because I learned recently that not everyone knows this. So I know Amy knows how to do this, but here's what it means to cut a deck of cards. Is you have your deck of cards, you take a portion of it and you move it over, and then you take the portion that you on the bottom and you put it on top. So it kind of mixes up the order of the cards some. Okay, so Amy, you can go ahead and do the same thing. So cut the cards and then completely cut. So here you go. I won't touch them again, I promise. So cut the cards, completely cut. Now give it over to Kirsten. Sorry, I almost messed it up. Kirsten can do the same. Go ahead and cut the deck if you want to. You don't have to, but if you, yeah, you can do that. Very good. And then Abby, Abby? Oh, amazing. Abby, you can do the same thing or not. It's up to you. So at this point, I have no idea what's going on with the deck, but go ahead, cut it one more time. And then you're going to pass it over to Kylie. Really? I was just making up words there. Kylie? Okay, Kylie. Do you like where the deck is now, or do you want to cut it as well? It's up to you. You can do whatever you want. If you trust Abby, leave it where it is. Okay, so Kylie's going to take the top card and then pass the deck back to Abby. And then you're going to take the next card, Abby. And then you're going to pass the deck back to Kirsten. Kirsten's going to take the next card. So we got 3 cards here. Now here's what I want to demonstrate. What I'm going to do is I'm going to do 3 things. I'm going to do 3 predictions here. I'm going to, with Kylie, sorry, I'm having trouble. With Kylie, what I'm going to do is I'm going to predict the suit that comes. Wait, you can look at your cards, by the way. Yeah, just want to make sure that you can look at your cards. You got your card? Do you know what suit you have? Don't tell me. Now, so I'm going to predict Kylie's suit. I'll ask her what her number or letter is. So what kind of card do you have? Like Jack, Queen, 2? What is it? What is it? It's a jack? Okay, so that's fine because I'm just going to predict her suit. And that's a 1 in 4 chance, right? A 25% chance. It's kind of like me rolling this die. Not very impressive. 25% chance. So 1 in 4 chance that I get the right suit. Now, with Abby, I'm going to do the opposite. I'm going to predict what number or letter, the face value. So you can just tell me your suit. So What is it?
Spade.
It's a spade. So she has a spade. I'm going to tell what number or letter it is. That's a little bit more impressive. That's a 1 in 13 chance, right? If I just guess. 1 in 13, that's a little bit less than 10%. Now, with Kirsten, I'm not going to ask her anything about her card. And I'm just going to tell her what card it is. And that's a 1 in 50 chance. Because now, you might say 1 in 52, but remember, I'm already going to predict those two cards. 1 in 50 chance for Kirsten, that's 2%. A 2% chance that, that I'm right. So let's go back to, Kylie. I've got cards in my head, I've got names in my head, and Kylie said that she had a jack, and I'm pretty sure that that is the jack of hearts. It is? Okay, very good. Okay, but it was 1 in 4 chance. It was a guess. Come on. 1 in 4 chance. 25%, not impressive. Okay, I'm going to try to impress Abby. That's a little bit more interesting because 1 in 13 chance. You believe you have an 8? Is it an 8? Okay, so she's got an 8 of spades, you said? Okay, 8 of spades. So 1 in 13, still not super impressive. Basically 1 in 10 chance. Now let's go to the 1 in 50 chance here, and I'm pretty sure that that's probably a red card as well. I'm thinking that it's a diamond. Don't tell me. Is it the King of Diamonds? King of Diamonds. Okay, very good. So thank you very much. You can just stack those up, and I will take them back in a bit. But that demonstrates. What I wanted to demonstrate with that is that we all have now. Some of you might have been impressed with the fact that I knew that was a heart over there, but the hearts. That was just a 1 in 4 chance, a 25% chance, not impressive. And then there was the 1 in 13 chance, 1 in 13 chance, that's roughly 8%, still not that impressive. Maybe it's more impressive. And then the 1 in 50 chance, that I think is where things get impressive. So here's what I wanted to do is make this on like a little sliding scale. You decide where you're impressed. Are you impressed up here? Probably not. Here, maybe, but here for sure you're impressed. So the lower the probability that I can guess what card they have, the more impressive it is that I got it right. That's what I'm trying to show you here. And this is the same thing that statisticians do. Here's the way statisticians think. They say, what are the chances that this particular researcher has it right? And by being correct, we mean that whatever their hypothesis is, that their hypothesis is correct. So maybe the hypothesis is that women do better on statistics exams than men. That's a hypothesis. Once we have that hypothesis, we could compute the probability. It's a little bit more complicated than the cards here. We could compute the probability that that researcher is correct. And then if that probability is low enough, then we're like, it's probably not that they guessed. They probably actually know what they're doing. So that's what this is trying to illustrate, is that you have to decide, where are you impressed, or where is this mind-blowing? Maybe it's never mind-blowing for you. Maybe you'd have to say, you got to go down to 1 in 100. That's fine. That's just who you are, So where would you cut off from just, you guessed, to, wow, you must be magical, which I'm not. There was a trick involved. I cheated. But anyway, so that's what that's supposed to illustrate, is that is, and now we have a word that we used to illustrate this. So generally, this is statistically significant, or just significant if it's in a statistical context. We would say something is significant. That's a significant finding. What that usually means is 5% or better. And what I mean by better is less than 5%. So if the chances that someone got lucky, like the chances that I got lucky with Kirsten was 2%. Chances that I just got lucky and guessed the card, 2% chance, then you say, you probably didn't just guess. You probably used some sort of a Jedi mind trick on her, or whatever, but or mathemagic, which is what I actually did. But anyway, so 5% is the cutoff. Anything less, usually, some statisticians say that 5% isn't good enough. They want it to be less than 2% or 1%. And if we go back to that study, you'll notice that that they have different numbers for different, you've got the 5% here, 0.05, and they say, hey, here's the way I would interpret this. They're saying, they're signaling to me, this probability is bigger than 5%, it's not impressive at all. I don't think that this is just by chance. Whereas over here, what they're signaling to me with that, here, I'll just zoom in, with this, is they're saying, look at this, whatever your bar, however low it goes, my probability is so low that it's even less than 1/1000. There's no way that could have happened by chance, is what these people are saying when they say this. So these probabilities, that's what they're referring to. So when you see this on your homework, you're going to see phrases like statistically significant. You're going to see p-values. They'll say that the probability is such and such. They're just referring to the probability that whatever happened just happened by chance. And if it's low enough, you say, it's not by chance. It's probably that there's something real going on. It's like when we have polls for the presidential election. You'll hear this idea of a margin of error, or maybe that this poll is just within the margin of error, so it's still a toss-up, even though whoever it is, candidate A has 49%, candidate B has 51%, or something like that. They'll say, well, that's just still a statistical dead heat. All that means is that by chance, because they're just choosing 1,000 people, not everyone, by chance they happen to be more people who support candidate B than candidate A in the poll. And that's all it is. It's just random chance. The probabilities aren't good enough. Now, when the difference between the two candidates gets much bigger, then you can say statistically that's a significant difference. And that just means that it's probably that it actually is true. It's not by random chance. Now, I know what you're thinking at this point. You're thinking, are we going to get back to that probability of dying? Well, we have to go through the other probabilities really quick. So you remember at the beginning, I had 4 questions for you. What's the probability of getting a rain? Rain, well, it's pretty much 0% today, I think. I don't know, I haven't looked at the Weather Channel, but it varies. So this is, of course, just an empirical probability based on what weather forecasters have seen in the past. And so let's see, it says 2%. 2% chance of rain today. Could happen, but probably not. It's about the same chances as me picking Kirsten's card if it was just by chance. Okay, next one. Getting an A. So this is a couple of years ago. I had 211 students. There's one year where I had, I think I taught 3 or no, it must have been 4. I had a lot of statistics classes. It must have been more than that. But anyway, so fall and spring. It wasn't all in one semester. But so I just took that one. That year, it was 49 of those students out of 211 got A's. So I don't know, is that about 1/4? So you got about a 1/4 chance if you believe that your class will be similar to them. Okay, on to the Powerball lottery. Here is your chances. Sorry, this should be equal here. So it turns out that there are, if you work out at least a couple of years ago, I don't know if it's still this way, but if you work out the way that the Powerball lottery is set up, there's 123,396,455 different ways of choosing your little numbers for the Powerball lottery, and there's the probability that you win is 1 out of that, because there's only one winning set of numbers out of this. Now, let's get to the real issue. What are the chances of you dying this year? Now, I must say that I've had to change my numbers from year to year, and so I'll warn you that this particular set of numbers is based on the CDC numbers. They publish something called the life tables, which is something of a misnomer, isn't it? If we're talking about the probability of dying, and literally on the top of the table it says probability of death. I'll show you. But anyway, so I've got the life tables from 2011, and I just this morning actually, well last night I did this, I updated my stuff to include 2021. So they publish these every few years. And so the numbers have changed slightly, and I didn't get to change this, but the numbers are not that different. So here's what this is. So this is directly from their tables, and this is for all males, and I've got females here as well, don't worry. All males in the United States. If you separate them by race, so the various races, you have differences that are concerning, of course, but I've just lumped everyone together here, and then you can look at the differences. By the way, well, we'll get there if we get there. Talk about the difference in the different races. So, how old are you? Well, you can find your age there and then find your probability. Now, this is based on 2011 numbers. 2021 has shifted a little bit, but not that much for your age group. So your age group is almost the same for that. So if you're a dude, you can see you've got, I'm guessing that you're somewhere in here, probably. And so it's, at the worst, it's 1 in 1,000. 1 in 1,000 chance? So if there are 1,000 of you running around, one of you. Hopefully not you, but anyway, there's those probabilities. Girls have it a little better. So here it's about half of the guys. I'll talk about that in just a minute. So there's the girls, same groupings. This is 18-year-olds, 19-year-olds, 20-year-olds, and you can go up and down to figure out. So yeah, not bad, right? If there's 1,000 of you, it may be that none of you die next year, because look, this is 3 in 10,000. So well done, girls. But anyway, like I said, I was updating these because years ago, this is in 2011, the numbers, and I have the 2001 numbers as well. I actually graphed the data. This is a graph of the probability of dying based on your age. And of course, being a baby is horribly risky. So don't do it if you can avoid it. So the babies, there's like a huge chance that they die in infancy. But then it drops down. The safest person, the reason I did this is because I was curious, who is the safest person in America? Turns out it's an 11-year-old boy. 11-year-old boy is, if you're an 11-year-old boy, you have the lowest chance of dying. Now, notice that the girls are red, the boys are blue, and the boys, guys, you're probably noticing this little hump here. You know what that hump is? That's that hump. You hear that? It's the stupidity gene. I know, guys, the stupidity gene kicks in around age 16, 17, and it turns off again around 25. So anyway, there's that stupidity gene kicking in, but then we never catch up. You know, we never catch up to the girls because there's some latent stupidity so we're always more likely than the girls. Now, here's the thing that I was fascinated by. I've been doing this, like I said, for like 27 years. I've been teaching statistics. And back in 2001, the safest person to be was a 10-year-old girl. Now it's an 11-year-old boy. So that's one fascinating thing. Another fascinating thing is the way that the graph has changed. Here are the graphs for 2001. You see the stupidity gene here. Kicks right in for the guys. Yeah, here's you see this, the 11-year-old girl right there, boys. I think this is because back in 2001, guys, you know, we were all outside, or you guys, well, your parents were outside climbing trees and hurting yourselves. Now the guys are inside playing Clash Royale. And it's the girls who are riding the unicycles and doing gymnastics. But anyway, so you can see there this interesting phenomenon. So 2001, 2011, look at 2021. Isn't that weird? You don't have that hump. I mean, you do have this sharp increase, but I think I figured out what's going on here. It's probably COVID. You see, these numbers are based on the previous year's mortality. So in 2021, the previous year was 2020, and so that messed up all the numbers. So for one thing, the guys weren't out there with their motorcycles killing themselves. They were staying home, I guess. You know, you didn't have people driving, and so the only thing that was killing people was other stuff, I guess. So anyway, I suspect that if we give it a few years, maybe in 2026 or 2029, we'll get back to this, guys. However, we don't want you to be in part of this hump. So, you know, take it easy when you're in your car and don't kill yourselves. Okay, so there's that. Oh, that's it. Okay, so homework, there's 4 sections. They're all different. do your best with them. There's like probability, there's some statistics, there's some weird stuff going on. Do your best. We'll pick up the pieces on Friday. I'm sure it'll be fine. And I'm going to turn off the recording if you need to chat. Otherwise, I hope you have a great day.